Let's talk about Rust. You know, most of the time, it's this super safe world where the compiler is basically your guardian angel, right? But what happens when you need to step outside that safety net? Well, that's what we're doing today. We're diving into the deep end, exploring the really advanced, super powerful, and yeah, sometimes dangerous side of Rust. Think of it as the coder's quest for forbidden knowledge.
And hey, this journey comes with a pretty serious warning. This is straight from the Rustonomicon, which is basically the official guide to Rust's dark arts. It says, should you wish a long and happy career of writing Rust programs, you should turn back now and forget you ever saw this book. Whoa. See, this isn't just about learning some new keywords. It's about a huge shift in who's responsible for safety. It goes from the compiler to you. So, you know what? Let's take that warning as a challenge. Let's dive in.
So, Section 1, Beyond the Safety Net. And it begs the question, right? Why on earth would anyone want to leave the comfort of the compiler's guarantees? The answer is, sometimes you just have to. Because while Safe Rest is amazing, some problems demand more. They need you to get way closer to the metal, to operate outside the normal rules, and to basically look the compiler in the eye and say, hey, trust me, I got this.
Okay, so when exactly isn't Safe Rust enough? Well, this list kind of hits all the major points. Think about it. Interfacing with other languages, like C, you're stepping into a world the Rust compiler has no idea about. It can't verify any of it. Or what about working with uninitialized memory, or writing super low-level stuff for an OS or hardware, and of course the big one, squeezing out every last drop of performance. In these cases, you have to do things the normal safety checker just can't understand. And this is where our quest really begins. All right, Section 2, the unsafe frontier. This is all about taking responsibility from the compiler. And this leads us straight to the first and honestly the most fundamental piece of forbidden knowledge we're going to talk about, the unsafe keyword. It's the gateway to everything we just mentioned, but it comes with a really, really serious contract. So what is unsafe Rust? I mean, does it just mean your code is automatically buggy or broken? Well, no, not quite. Okay, so here's the key thing to get. The unsafe keyword doesn't just turn off the borrow checker or the compiler. Not at all. What it does is it gives you a few extra superpowers inside a special block of code. Things like dereferencing raw pointers or calling C functions. But in return, you are making a solemn promise to the compiler. You're saying, hey, I have personally checked this, and I guarantee it won't violate Rust's memory safety rules. Basically, inside that unsafe block, you are the borrow checker. And man, the Rustonomicon does not pull any punches about what's at stake here. Get it wrong, and you are right back in the land of seg faults and all kinds of undefined behavior. But get it right, and you unlock this whole new frontier of performance and what's possible. It's really the ultimate trade-off, isn't it? Power for peril.
All right, Section 3, Meta Programming with Macros, or as I like to call them, spells of automation. So, if unsafe is about taking responsibility away from the compiler, our next topic is kind of the opposite. It's about giving the compiler brand new instructions. We're talking about macros. And this is where we get into metaprogramming, the art of writing code that writes other code for you.
Just think about that for a second. You're not just writing your program's logic. You're writing logic that generates even more logic. And it all happens at compile time. It's an incredibly powerful way to get rid of repetitive, boilerplate code, and you can even invent what feels like totally new syntax for the language.
So you might be thinking, okay, but why not just use a function? Great question. The big difference is when they do their work. A function gets called at runtime, while your program is actually running. A macro, on the other hand, gets expanded at compile time, before your program is even a finished thing. And this lets macros do stuff that functions just can't. Like they can take a variable number of arguments. You've seen this with println or vec, right? Or they can just generate entire trait implementations out of thin air.
And in Rust, there are basically two families of macros. First, you've got declarative macros, the ones you make with macro rules flen. They're kind of like a find and replace on steroids, matching patterns in your code. The vec macro is the classic example. But then you have procedural macros. These are the heavy hitters. They are literally Rust functions that take your code as input and spit out new code as output. This is the magic behind every single custom @derive attribute you've ever typed. Okay, Section 4, Racing with Tokyo's Scheduler, the engine of speed. Look,
theory is great and all, but let's see how this stuff actually works in the real world. And for that, we're going to look at Tokio, which is Rust's go-to high-performance asynchronous runtime. Its scheduler is it's a masterpiece of low-level engineering that uses these dark arts we've been talking about to get absolutely insane speeds.
So get this. When the Tokyo team decided to rewrite their scheduler, some of their benchmarks didn't just get a little bit faster. They saw a 10 times increase in performance. 10! How was that even possible? Well, it's not magic. It's something called mechanical sympathy, this incredibly deep understanding of how the software and the hardware are actually interacting with each other.
And I mean, just look at these numbers. This graph shows the impact perfectly. We're looking at a benchmark called chained_spawn, and it just hammers the scheduler by creating new tasks over and over again. The old scheduler took over 2 million nanoseconds per iteration. The new one, under 170,000. That is just a colossal drop. And it all came from completely rethinking how the scheduler was designed from the ground up.
So what was the secret sauce? How'd they do it? Well, the whole theme was just reduce. Reduce communication between threads, reduce memory allocations, reduce atomic operations, anything that could cause a slowdown or contention. They built a brand new, way better work-stealing queue, and yeah, that required some very careful, very well-audited unsafe code. The whole goal was to get rid of every single bottleneck. Because, as the Tokyo devs put it, and I love this quote, there is no code faster than no code. All right, section 5, pinning down memory, mastering the deep magic. So to really get how something like Tokyo Scheduler can be both blazing fast and safe, we have to go even deeper, like way down into Rust's memory model. And this brings us to probably two of the most advanced topics in the entire language, pin and variance. These are the deep, deep rules that govern how memory and lifetimes actually behave. So let's start with the first question. What on earth is pinning? Okay, so in Rust, values can get moved around in memory all the time. The compiler does it, you do it, and usually that's totally fine. But what if you have a struct that contains a pointer to another part of itself? Well, if you move that struct, that internal pointer is now totally wrong. It's pointing to garbage. And that's what pinning solves. Pin is basically a contract you make with the compiler that says, I guarantee this value will not be moved from this spot in memory. Ever. And this is absolutely critical for modern Rust, especially for async functions. See, under the hood, an async function gets turned into this big state machine that refers to itself all over the place. If that state machine got moved, everything would break. Pin is what prevents that disaster from ever happening. The analogy here is just perfect. Think of pin like a thumbtack you're sticking into a corkboard. Once you pin that piece of data, you know for a fact it's not going anywhere. You can safely rely on its address. And this leads us to the other deep magic, variance. Now this one's a bit more subtle, but it's super important. It's a set of rules that's kind of the foundation for Rust's entire lifetime system. It's the reason why shared references are so flexible, what's called covariant, meaning you can use a long-lived reference where a short-lived one is expected, but it's also why mutable references are so strict, or invariant, which is what stops you from accidentally creating all sorts of nasty bugs. It's the deep logic that makes the whole borrow checker work. Okay, final section, forging safe abstractions, the true purpose. So wow, we've journeyed through unsafe code, metaprogramming, crazy fast schedulers, pinning. It can kind of feel like we've spent this whole time just learning how to break all the rules, right? But that brings us to the final, and honestly, the most important point of this whole quest. What's the true purpose of all these dark arts? I mean, why does Rust even give us these seemingly dangerous tools? What's the endgame here? And here it is. This is the whole point. You don't use these tools to write a giant, totally unsafe application. No way. You use them in a tiny, meticulously checked, carefully audited little corner of your code to build something new. Something like the Tokyo runtime or a brand new data structure. And that new thing, it presents a 100% safe, easy-to-use interface to everybody else. So the dark arts aren't about leaving safety behind. They're used to expand the world of safe Rust. And that's the philosophy that ties this all together. The goal is to be fast and correct. It's never about just being fast by throwing safety out the window. It's about using these advanced, incredibly powerful tools to build foundations that are both blazingly fast and provably correct. So you see, this whole quest for forbidden knowledge, it's not about breaking Rust. It's about making it even more powerful for everyone.